Hey everybody, this is Miss Phoebus, and this is Lesson 9. We are talking about ancient Mesopotamian mathematics. So, Mesopotamia is the region between Africa and Asia, and we got a little bit of Turkey. We are kind of looking in this green area around Iraq, Saudi Arabia, Iran, and so you can see in this map some maybe some familiar names like Syria. You hear a lot about that in the news. Babylon, that is talked about in the Bible. You can see on the bottom lower corner of the map, you see Egypt with the Nile River. Kind of up and to the left off the map, you've got Greece coming a little bit in where it says Hittite Kingdom, and Anatolia, that's Turkey. So we are around this region, and it is called Mesopotamia, or the Fertile Crescent. You may have remembered that from middle school. They usually talk about that. And civilization arose here because there was really fertile land because of the two rivers that are running through that green part, the Euphrates and the Tigris. And so that allowed for agricultural innovations to take place, and people started settling down and building cities and towns, and it kind of boomed. Nowadays, it's pretty desert, but back in ancient times, this was a lush place to be. All right, Sumerians were the first urban civilization in the historical region. They were in southern Mesopotamia. Scholars argue that they can be found far back as 3,500 BC. And Sumer is the birthplace of writing, the wheel, agriculture, the arch, the plow, and irrigation. So many things that we use today are used are from the Sumerians. So you want to talk about agriculture, the wheel. We couldn't drive without the wheel, right? So lots and lots of innovations. The Babylonians came along a little while later in the same-ish region. They're a little bit more in the central region. And Babylonia emerged as a major power when King Hammurabi, you may have heard of the Hammurabi Code, created an empire out of the territories of the former Akkadian Empire. So Babylon got to be pretty big in its day. So these two civilizations kind of go together. The Babylonians got a lot of stuff from the Sumerians. So we know about an early writing system from 3,500 BC. And if you notice, you've got things that start off looking almost like hieroglyphs. They call them pictographs. So like head, if you look in that first column on the left, head looks like a head. To walk looks like a leg and a foot. A hand kind of can make out some fingers. Barley looks like grain. So they start off looking very much like the object that they are describing. And then in the 3000 BCE era, looks like everything gets turned on its side. And then in the 2400 BC era, we start getting more abstract. You can definitely tell the similarities between the middle two columns, but you're starting to get more sharp angles, not as many curves, and it's looking a little less like that object. And then with the far right column, you're getting these triangular looking things at the endpoints, and that goes into the cuneiform, the wedge writing. They're actually pressing a stylus that has a triangular kind of tip into clay and then baking that clay to make it harden. But if you look at that right column, we are very far from the original pictographs. So they've created these symbols over time, and they kind of morphed into something that doesn't look so much like a picture anymore, more of just a symbol to represent that. All right, we're going to look at ancient Sumerian, and both Babylonians later adopted this system of writing numbers. 0 came much, much later. 1 through 60 or sorry, 1 and 60 look the same. So you pretty much restart your number system. And the system was the first to have place value. So I like to look at these things when you get to like 10. I like to think of it like a little fishy kind of swimming along. And then these ones, I think of them as triangles on a stick. We're going to look at a couple different fonts. So you had to have really good handwriting back then so you could tell what they were. Some historians have argued that the number 60 has many factors, and so that's why the Sumerians and then the Babylonians used a base 60 numbering system. So the factors of 60, numbers that multiply to 60, are 1 and 60, 2 and 30, 3 and 20, 4 and 15, and 5 and 12. So all of those number pairs, multiply to give you 60. That means 60 can be divided by lots of things. And so if you're dealing in multiples of 60, you can divide and deal with fractions a lot easier as well. So having so many factors made 60 a number that is easy to divide into different amounts. And then the system of weights and measures in the Fertile Crescent civilization relied on fractional amounts of 1/3 and 2/3. So 1/3 of 60 is 20, 2/3 of 60 is 40. So that would make the number 60 easy to manipulate when looking at amounts of grain that you're using to barter with. Others argue that the Babylonians and the Sumerians were really concerned about how many days there were in a year, and they put 360 days in a year, so that might help with using 60 as a base system so that you could maybe work with a calendar a little bit easier. There's a video that I put on this page that shows you how to count to 60 on your fingers. So that might be interesting, and that might be a reason why that they use base 60. But we're not 100% sure why civilizations in Mesopotamia use 60 as a base. We use base 10, and base 10 because we have 10 fingers. So why base 60? We're not really sure, but there are a couple theories out there. All right, so we're going to look at take a closer look on these numbers, look at how their number system works. The rightmost column, so let's look at 31. The rightmost column is the ones, and then the one on the left, that's going to be your tens. And so you would use that until you got to 60, and then numbers bigger than 60, we have to create almost like two values, and we have to figure out how to write these numbers based off of how many 60s that we have. So one of the things that I like to do is I like to have a calculator handy, especially if I am trying to figure out how to write these numbers. But as we go, we're going to see that we just keep extending the left side to create larger and larger numbers. And they used pretty large numbers. We'll talk about that in the next video. All right, so reading numbers, if you notice I have several different fonts here, and you have to use spaces. So we're going to cut these here. So each of these, we have basically 4 values. What's going to go on here is going to get multiplied times 60 to the 0. What's going on in there will get multiplied times 60 to the first. What's going on in here will get multiplied by 60 squared. And what's going on here will get multiplied by 60 cubed. We'll figure out what each of those numbers are. We have splits here and here and here. So again, we're going to multiply this right side by 60 to the 0. 60 to the 0 is 1. Here we'll multiply by 60 to the first. Here we'll multiply by 60 squared. And here we'll multiply by 60 cubed. So if you don't have a calculator out, you might want to grab one. All right, we're going to have a break here and here, I think. 60 to the 0, 60 to the first, and 60 squared. So let's try to figure out what these numbers are. So for this one, I have 2 triangles. Notice these triangles aren't on a stick, but that's okay. 2 triangles represents 2. 2 times 60 to the 0. We'll figure out what that is later. Now, what we're going to do for this is we're going to figure out how to write that with our 60, and we're going to add it to our 2 times 60 to the 0. So this is 1, get rid of this, because there's one triangle. There's 1, so this is 1 times 60 to the first. All right, then I pick up my little triangle fishy guy. That's 10, so we want 10 times 60 squared. And then for the last part, we have 2 fishies and then 4 triangle stacks. So 2 fishies is 20. So it looks like I'm right here at 24 times 60 to the third. All right, I'm breaking out my calculator. 24 times 60 to the third is 5,184,000. All right, 10 times 60 squared is 36,000. 1 times 60 is 60, and remember this becomes a 1, so 2 times 1 is 2, and then we just add them all together. 62, I get 5,220,062. So that is how the ancient Sumerians and Babylonians dealt with their numbers. Now you might be like, hey, that's a lot of work. But you have to think, back in those days, they didn't have calculators. They had people sitting around calculating things. Also, they came up with this number system. They worked with it all the time. I mean, how do you know what the symbol means? Because you learned it. You work with it all the time. So how do you know what this symbol means? If you work with it all the time, you know how to deal with it. But there was probably a population that was a bit more educated in the numbering system, and probably that was their job, was working with numbers. All right, let's try to figure this out. These are my little fishy guys. Looks like there's 4 of them stacked, so I'm going to be dealing with this number, 40 times 60 to the 0. All right, and then we're going to do the same kind of thing, same stack of numbers, but we are dealing with 6 little triangles. So that's going to be 46 times 60 to the first. And then I've got 5 little triangles with a stack, or no, 5 little fishies with a stack of 9 guys. Nope, that's not 9. 7. 57 times 60 squared. All right, and then there's just 1, so this is 1 times 60 cubed. We're just going to add all those together. All right, so 60 cubed is 216,000. 57 times 60 squared is 205,200. 46 times 60 is 2,760, and then this is 1, so 40 times 1 is 40, and then we just add them all together. Again, I'm just typing it in the calculator, so don't think I'm doing this all in my head. All right, I get 424,000. That's it. Okay, so these are our numbers that we are dealing with. All right, we got one more. If you think you can figure out what's going on, why don't you pause the video and see if you can figure out how to read this. I've got it split up for you. All right, starting at the right, it looks like I have 4 little triangle guys. That's 40 times 60 to the 0. And then I have 2 little fishy guys and 6. That's going to be 26 times 60 to the first. And then I've got 4 little fishy guys and 4 things. That should be 44. So this is 44 times 60 squared. Plus 26 times 60 plus 40. I get 160,000. Okay, so you have to do a little bit of math with that base 60 number system because we are not a base 60 number system. We are a base 10 number system. So this is not familiar to us, so it's a little bit more work. right. Oh, look. We did it right. Nice. Love it. All right, let's try to write with cuneiform numbers. So we're going to start off with 23, and 23 is actually in this. So we're just going to write what we see. So we're going to practice what we can do. So we got some little fishy guys, 2 of them. And then I got some little triangles on a stick. If you don't want to draw the sticks, that seems to be okay. It's not the way that you did it. But it's definitely, you want to kind of try to make them the same. Okay, let's look at 185. Now, 185 is not on here. So what I'm going to do is I'm going to divide 185 by 60 and figure out, it's much larger than 60. So this has got, it's 3, remainder 5. So what I want to do is I want to do 3. And so this is 3 times 60 to the first, and then I want to leave a spot and then do kind of a space. And then I want to do a stack of 5 guys. 5 guys. Okay, so that is 5 times 60 to the 0. So dividing would allow you to be able to figure out your numbers. Make sure you leave a space in between. All right, so what I'm going to do is I'm going to do divide by 60. So 556 divided by 60 is 12. It goes in evenly 12. 12 times 60 is 720. I need 36 to be able to get to the next set of 60. So I need to do a 12 first. So that's a little fishy guy and triangle on a stick. All right, I'm going to leave a space, and then I want to do a 36. 1, 2, 3 fishies, and then my triangles on a stick. And then make sure that there is a space. I don't know how I'm going to do this. Make sure there's a space in between. Space. Don't write space. And make sure there's a space in between. So that this is 12 times 60 to the first, and this is 36 times 60 to the 0 power. That's kind of fun, a little bit. So they come up with one of the first number systems that we know about, really. Well, and the ancient Egyptians are kind of at the same time. All right, but the Sumerians are developing a complex system of metrology, which is the science of measuring things. So if you see, we've got things like grains, fingers, hey, foot. You may have heard of cubits, sorry. So there are some things in here that kind of follow through into our system of measurement itself. I think they use cords in the Navy. I'm not 100% sure. A nation system of measurement does not necessarily reflect what the notation, like the numbers themselves, are doing. So sometimes they're completely separate. So this is ancient Mesopotamian links that we know about. These are ancient Mesopotamian areas. I like that they call things gardens, fields, and estates. Makes it sound like it's getting from small to bigger to biggest. But they are measuring area. They're measuring time. If you notice, there are some words in there that we do know. We don't know the Sumerian, but it translates into watch, day, month, year. Don't know what a gesh is. Maybe it's a second or something like that. But 1 year in Mesopotamian units of time is 360 days. So then they started dividing that 360 days to create those units of time. Now, back in the day, Sumerians only did 12 hours in a day, but at some point they changed it to 24. So Sumerians are known, and Babylonians even too, Sumerians are known for their clay tablets. So they would just have, like I said, they have people that would just sit around and calculate things all day. So this is probably some of their work. They have multiplication tables, they have division tables, geometric exercises, all kinds of different things with squares and cubes and square roots, areas of triangles and volumes of cubes. So they're writing lots and lots of stuff down. The Egyptians wrote stuff down too, but because they did it part in stone and part on papyrus, the papyrus didn't last, so we don't know as much about their mathematical works. But because of the clay tablets, we do know quite a bit about the Sumerians. Later Babylonian tablets cover topics like fractions, algebra, measuring, methods for solving linear, quadratic, and even some cubic equations. Looking at numbers that multiply together to give you 60, working with Pythagorean triples, looking at the square root of 2, tables of compound interest, and a really, really good approximation for pi, especially for the time that they lived in. There is a Babylonian tablet that's pretty famous called the Plimpton 322. It is known for being a list of Pythagorean triples, and somebody just sat around and figured out all of them. But it wasn't a brute force method. It wasn't like they just like sat around and tried every single thing. They found a pattern to it. We're going to see if we can figure out the pattern as well. But a Pythagorean triple, these are all positive whole numbers, positive integers, okay, that fit a squared plus b squared equals c squared. That is something that you should know from middle school. And the most common one is 3, 4, 5. So that if I take a squared plus b squared equals c squared, c has to be the hypotenuse, the longest side. Use. Okay, so 3 squared plus 4 squared has to equal 5 squared. Well, that's 9 plus 16. Does 9 plus 16 equal 25? Yes, it does. Okay, so 3, 4, 5 is a Pythagorean triple. Now, we're talking about Pythagorean triples long before Pythagoras, long before. Okay, so that means that they knew stuff before the Greeks did, but we attribute a lot of the stuff to the Greeks because they proved it to be true. This table doesn't necessarily prove it to be true. They just went through and found things that worked, and probably by looking at the patterns. So if you use sides 1, 1, and square root of 2, those aren't Pythagorean triples because the square root of 2 is not a whole number. It is a decimal that never ends and never repeats. So the triples listed on the Plimpton 322 are too many to have been constructed by brute force. From a modern perspective, a method of constructing such triples is a significant early achievement known before only among the Greeks. So we used to think the Greeks were the first ones, and then we found the Plimpton 322, and we were proved wrong. So we're going to look at how to find additional Pythagorean triples. We're not going to go too far out. We know that 3, 4, 5, and I'll go ahead and tell you 5, 12, 13 are Pythagorean triples. And let's look at why. Okay, so here what we're doing is we're taking sides, like 1 squared is 1, 2 squared is 4, 3 squared is 9. And we're looking at difference, like 4 minus 1 is 3. And then 9 minus 4 is 5. And then 16 minus 9 is 7. And if you notice, every time you subtract these square numbers, you're getting the next odd number in a sequence. Well, if the odd number is a perfect square, that means that 9 plus 16 equals 25. That's your 9 plus 16 equals 25. Your 3 squared plus 4 squared equals 5 squared. So if you are looking at all the numbers after they're squared and then compare the differences and look for a perfect square in the differences, you're going to be able to figure out what squared plus what squared equals something squared. So let's see if we can find some more. So we know 14 is 196. Oops. Let's do it this way. 14 is 196, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Let's see what we can do. Okay. So we're going to look at squaring these values. So 15 squared, I've got my calculator out. So 225, 16 squared. 256, 17 squared, 289, 18 squared, 324, 19 squared, 361, 20 squared, 400, 21 squared, 441, 22 squared, 484, 23 squared, 529, 24 squared, 576, 25 squared is my favorite, 625, 26 squared, 676, 27 squared, 729. Do you see what I'm doing? I'm just squaring the numbers. Alright, so somebody did this and figured out what number times number is, and I'm sure they had some sort of multiplication system. And then we're going to subtract. So we know the distance between 13 and 14 is 27, so that would mean this is 29, 31, 33, 35. Now we're going to skip over 36, which is the next perfect square, because these guys are all odd. All right, so the next one coming up should be 49. So right here. So if I subtract, well, not subtract, but it's these two. If I do the 500, actually I should have brought this, the 576 minus the 529, I get, oop, no, that's wrong. That's not right. And I did a lot of drawing on here. Okay, so it's the 625 minus 576. Yeah, right here. So these guys, when I subtract 625 and 576, I get 49. So that means 49 is 7 squared plus 24 squared. Let's try that again. Equals 25 squared. So that is a Pythagorean triple. So that means that the next values that I get, and I should probably be writing these in between, so like 49 should be here. Okay, the next one is not going to be 8 squared because we're only using odd numbers. So the next one's going to be 9 squared, which is 81. I don't know. This would be 51. This would be 53. This would be 55, 57, 61, 63, 65, 67. We're close. I'm going to get rid of these and kind of come over on the left and keep going. So what I'm going to do, we're on 34, 35, 36, 37, 38, 39, 40. We know that there's going to be a number squared, but let's look more at, can we figure out where 81 is going to happen? So that would be 69, 71, 73, 75, 77. No, between, hang on a second, between 34 and 35, that is 69. Here is 71, 73, 75, 77, 79. We're close. So it's the next one. So it is 40 and then 41. So let's look at 40 squared is 1600. 41 squared is 1681. Oh, 1681 minus 1600 is 81. That's a perfect square. That's 9 squared. So 9 squared plus 40 squared equals 41 squared. Woohoo! We found it. It was a little bit of work, but it didn't actually take us that long. And so somebody sat around squaring numbers on this Plimpton 322 and found numbers that worked, not necessarily tried every single number, but they found a pattern. And That's what we think has happened with those. So we have right triangles, 3, 4, 5, 5, 12, 13, 7, 24, 25, and 9, 40, 41. And so there are others out there. But the thing is that you have to be able to see if you can figure out what the pattern is. All right. Sorry that the video didn't work or the audio wasn't really good in the last video. Hopefully it works out this time. Bye, guys.